Hello, I'm Ed Butler from the Australian Institute of Marine Science in Darwin. My presentation is on a research proposal for nutrient cycling in tropical harbours. The structure is as shown here, beginning with the question, why tropical waters? Moving on to a background on nutrient cycling and gaps in knowledge, with an example from our home waters here in Darwin Harbour with nitrogen. Second part of the talk introduces a concept for a coordinated study within the World Harbour project, looking at several harbours, and I'll wrap up with ideas for research activities. Why tropical waters or harbours? Nutrient cycling in tropical systems is underrepresented in global literature. My sources are the Web of Science and Google Scholar, but these same sources indicate growth in studies of nutrients in the tropics over the last decade. In comparing tropical with temperate nutrient cycling in coastal and estuarine waters, there is greater nitrogen fixation, greater input of riverine nitrogen into these same systems. With more extensive marine carbonates, there is greater storage of phosphorus in sediments, greater total suspended solids and reactive silicon concentration in waters, and interestingly diminished nitrogen and phosphorus concentrations in the same waters. Mangroves dominate the intertidal region, and there is more extensive seagrass and benthic microalgae. Nearshore tropical ecosystems are similarly more susceptible to loading of nitrogen. An example comes from Corridor and colleagues' work, and with their suggestion of fragility of denitrification in tropical systems. And of course, tropical harbours bear the brunt of our inputs of nutrients. Here we have shorthand depicting nutrient cycling, in this instance nitrogen. The monotone arrows are loads or fluxes of different forms of nitrogen per the key to the right. Firstly, we're depicting historical situation. The width of each arrow represents approximately the loading distilled from various reference sources. In other words, this is representative, not definitive information. Note I've multiplied the riverine atmospheric inputs by 10 for clarity. 2 or 3 tone arrows portray transformations. An example is the yellow-green arrow from the atmosphere to the sea surface is nitrogen fixation. In the next panel, current end cycling is depicted, obviously with the human influence. We have greater riverine and atmospheric inputs, and that's both in magnitude and speciation. And as I mentioned previously, a possible outcome of this in shallow coastal waters is a negative influence on denitrification from the increased sedimentation and possibly ramifications of different nitrogen speciation in the inputs. Zeroing in now on Darwin Harbour. The harbour has on its shores a relatively young city and a small population, particularly in contrast to other tropical ports. It is distinguished by its very seasonal, wet, dry, tropical climate and, of course, its macro tides. In terms of size, it is a large harbour with a surface area several times, say, that of Sydney's. And as an aside, real-time data is available from the website shown, which comes from a buoy in the outer harbour. This next slide provides a snapshot of harbour water quality in the wet and dry seasons from past AIMS work. It presents mean data from 9 stations spread throughout the harbour. Turning to the nutrients, the difference between total dissolved N and the dissolved inorganic forms Ammonium nitrite and nitrate is of course dissolved organic nitrogen. It dominates over both dissolved and particulate N. With phosphorus, it is the same story. Dissolved organic P is dominant. It must be said in passing that DOP can include some polyphosphates. Comparing between wet and dry season data, the nutrients are seen to be depleted during the dry season relative to the wet. With increased light and slightly higher concentrations of chlorophyll during the dry season, this nutrient depletion is related to biological uptake. Present day monitoring is carried out by a Territory Government Agency over 80 surface water sites as shown in this map. It includes the harbour waters and some feeder streams. Measurements are constrained to inorganic nutrients and chlorophyll A, and dry season neap tides are favoured for evaluation of baseline conditions and discerning long-term trends. The next couple of slides show how we've built up a picture of nutrient cycling in Darwin Harbour. It is a nitrogen limited system. This has been determined from both observed nutrient ratios and laboratory incubation experiments with nutrient spiking. Upstream is heterotrophic or detrital processing. Here there's low light, high organics and high suspended solids. Downstream, in the outer harbour, is autotrophic, brought about by high light, low organics and low suspended solids. Seasonally, there is nutrient loading in the wet season and its processing in the dry. Mudflats are a site for nitrogen fixation, bringing nitrogen into the system, whereas mangroves are an effective filter and sink for the nutrients, perhaps with a little leakage of particulate organic carbon and nitrogen in litter. Variable top-down and bottom-up controls seem to modulate primary productivity in the harbour's water column. In this diagram, we have captured our learning in a conceptual model of nitrogen cycling in Darwin Harbour. A slightly different schema and key is used, but still the monotone arrows are fluxes and multicoloured ones represent processes. I'm pointing out now a number of subclasses of food web in the waterway. In the murkier landward waters, the detrital food web is favoured. Seaward, there are examples of a pelagic food web with plankton at its base, and on the sea floor, reefal and sponge examples. And of course, with most of the harbour fringed by mangroves, this ecosystem is crucial in processing nitrogen and other nutrients. An arrow with a question mark denotes a process that is unquantified. In the next slide, we're going to explore some of these gaps. Denitrification is probably the most pressing question, but there's also the bioavailability of DON and PN, the importance of the detrital food web, among inputs, atmospheric deposition. Other than nitrogen, dissolved organic P requires more study. There's limited information on reactive silicon, and the micronutrients, for example iron and zinc, are scarcely known. Iron is important in nitrogen fixation by microorganisms, and zinc is a cofactor in alkaline phosphatase that is critical in the recycling of phosphorus from DOP. I'm now going to focus on one of these and delve a little more deeply into it. The example I'm going to choose is the bioavailability of DON. I've earlier pointed out the importance of DON in the speciation of nitrogen in the harbour. It is either allochthonous, coming external to the waterway, or it is autochthonous, being produced within it. DON also spans different phases from truly dissolved through colloidal to particulate. Then there is the crucial question of bioavailability. Small molecules such as amino acids, amines, and urea are readily bioavailable, but larger macromolecules that are colloidal or particulate in nature, such as humic substances, are typically unavailable, often being referred to as refractory. Turning now to sources. Most autochthonous dissolved organic nitrogen, that from microalgae, be they pelagic or benthic, and possibly seagrass, is bioavailable. Other possible sources within the water column, such as corals and sponges, the DON characteristics are poorly known. Turning to allochthonous material, and particularly that from the terrestrial side, most of it is refractory, and I've just given the example of humic substances. In the coastal ocean, about 1/3 of dissolved organic nitrogen is estimated to be bioavailable, and in a recent view by Lomborg and Alvarez Salgado, it has been suggested that there is a bioavailability gradient for these organic forms, P greater than N greater than C. A result of this reactivity gradient is that the processing of organic material within estuaries produces material for export that has changed ratios P to N to C. An example in such as Darwin Harbour are mangroves that retain organic material and process it over extended periods. As a result, the organic matter exported from mangroves tends to be very carbon rich. Water quality models benefit from partitioning of dissolved organic nitrogen between labile and refractory forms. This requires a straightforward observational or analytical experimental approach to partition the DON effectively between these two forms. The mineralisation of dissolved organic nitrogen, its breakdown, especially larger macromolecular forms, and for that matter too particulate nitrogen, delivered in the wet, is fundamental to the supply of bioavailable N in Darwin Harbour. Although the processing can take place in microzones around suspended solids, the bulk of it will take place within surface sediments. I have here a temperate example of such, but it will apply just as surely in tropical estuarine sediments. The plot shows diagenesis of small organic nitrogen molecules, amines, into the sediment. The different symbols represent methyl, ethyl and propylamine concentrations in pore waters. The larger propylamine, the green dot, is exhausted first, followed by deeper into the sediment ethyl and then methylamine. As a result, there are increasing levels of the final product, ammonium, down into the sediment. and is shown by the grey line. Of course, this is the most bioavailable form of N and can diffuse back into bottom waters to be readily assimilated by microorganisms there. I'm now moving on to part 2 of the presentation, the opportunity from the study of nutrient cycling in tropical harbours under the World Harbours project. My recommended project goal is shown here. It involves 2 steps. The first is the gathering of new information on nutrient distribution and cycling within the project harbours, and following from that, advanced ecological solutions and the building of a resource for environmental management of nutrients within these harbours and beyond to other coastal systems in the tropics. My initial suggestion for harbour study sites are these 3: Singapore, Jakarta and Darwin. They offer a very useful spread of tropical climate types. They have quite different tidal ranges, and they certainly have different population pressures. Of course, the project in its later stages can be extended to other relevant harbours within WHP. Here are some ideas for research topics in these 3 harbours. The first relates to climate and specifically the effects of the monsoon, both within year variability across the 3 tropical subclimates and out to interannual variability. Mangroves form a keystone ecosystem and habitat across the tropics, and their capacity and capability as nutrient filters and processors requires further elucidation. The next 2 dot points relate to inputs. The first, nutrient composition in runoff as a function of both catchment and its extent of development. The second is atmospheric deposition as a diffuse source both locally and regionally. Structure of microalgal communities in the tropics is likely to differ quite starkly from those in higher latitudes and is certainly worthy of study as a function of nutrient supply. Finally, a constant activity within harbours, the effects of dredging and its influence on the release of benthic nutrients is the final suggestion. Outcomes from the nutrient cycling project can be to the considerable benefit of tropical ports, but also to coastal management across their home nations. Examples are mangroves and salt marshes, appreciated for their role as coastal buffers and providers of wide-ranging ecosystem services. Marine biota utilised to improve environmental quality and with potential spin-offs for agriculture. The use of calibrated and validated models for environmental management and scenario testing, feeding through to evaluation of nutrient assimilation capacity and identification of trigger thresholds. And finally, as a means of community education and consensus building. I would like to acknowledge the following people and organisations for contributing to this presentation. And thank you for your interest.